Uh, Good morning, everyone. So I hope we still survive. And okay, this is to complete the argument yesterday about to show that that the correlator of the chiral operator, namely we focus on trace lambda lambda, is independent of these coordinates. Okay. So what we do is that this is the two first blackboard is essentially the same as yesterday, just improvement of the notation. So instead of writing trace W square, I write it as S. Okay, S is a chiral field, so it satisfies this condition. I should remark that this is not just true. This proof is true for general chiral operator, not just S. There is no way that I have to specify what S is. As long as it satisfies this condition, it will do. Okay. So this condition, I have to remark you that this is by definition what we state as a chiral, the statement of what definition by definition what chiral field is. There is another definition which equivalent to this. Some people say that chiral field is something that annihilates by one supercharge, one of the supercharge. This is also equivalent definition. So you observe one thing, that supercharge and the superspace derivative are one-to-one correspondence. Indeed, this is the argument that I'm going to use, that SUSY generator can be viewed as differential operator associated with the superspace derivative, so a one-to-one correspondence. Okay, and this is crucial. So okay, let's proceed for now. So this is the bracket of dd bar. Okay, you can convert it into space-time derivative. Okay. And to compactify the notation, let's write it like that. There's nothing, this is just a notation, okay? So to avoid writing sigma mu every time, basically, this is just to avoid it. Okay, so we have this thing. So we use anti-commutator and we use this. So we arrived at this. This is yesterday. Now for simplicity, let's consider you take derivative with respect to x1. You can do it for any xj easily, but let's do for x1, okay? Then you use this identity. Of course, you will act on this guy. Okay. Now you use Lightness Rule. Pull this out in the front and subtract. You discover that by distributing d bar inside, when d bar hit the S, and S is a chiral field, you get 0. So this second line vanishes. Okay. Now you're left with the first one. The first one is the gist we obtained yesterday. The claim was this is 0. Yesterday I made two restrictive statements, as many observed. So first of all, yesterday I write it as x, and I said 1-point function is 0 and it's scalar. And the objection were, this is not a scalar operator and it's not a one-point function. Okay, fine. I admit that this is too restrictive for our purpose. But the statement is still true, provided that you have d alpha dot. Okay, why this is true? Again, you use the correspondence between the SUSY generator and the superspace derivative. You can write this as the insertion of the Q bar, and you observe that if you have a SUSY vacuum, SUSY vacuum has to be annihilated by a supercharge. Okay, this is by definition of SUSY vacuum. So this is how you construct a multiplet, basically. You regard Q as the annihilation operator. So it hits 0. You take the bar, you get this one. And then immediately you get this thing. Okay? So what we have shown was that this is 0. And indeed, you can generalize to any xj. Okay? And yes. So once you do this, you take the lowest component, you get what I would like to show, which is that this is independent of x. And observe that this is true for any chiral operator, not just S. So this proves also the fact that endpoint function of the chiral operator has no short distance singularity. This is a very important theorem. So let me tell you the history. This is have a long history. This argument was shown by 4 people, which we will mention later, is called N, S, V, and Z. This is Novikov. S is Schiffman. Schiffman, Weinstein, and Sakharov. Okay, but the cleaner version of the proof is due to Cacciazzo, Douglas, Seiberg, and Witten in 2002. Okay, and you can find several arguments in several papers, but this complete argument, you have to read many papers and then put them together, okay, just to tell you. Okay, so since this will close the section on gauge-Gino condensation, I would like to move on to the another very interesting development in supersymmetric field theory, namely the Witten Index. This is a really important topic because nowadays you might have heard the recent research that people compute something called the index all the time. So this is perhaps one of the oldest version of the index that you can study. The development is in the context of dynamical supersymmetry breaking, which I will explain why. Okay. Proceed. Okay, and as usual, my note is updated daily. Okay, so we move on to the Witten Index. Okay, so the idea is the following. The idea is that, as you know, that n equal to 1 super Young mills, you have dimensionless coupling, dynamically generated the scale lambda, big lambda that we have. In order to control the theory, Witten come up with a very clever idea of putting this thing in the box. Okay, you have more scale, namely the size of the box that you put in, okay? And you use this size of the box to control dynamics of the theory. It's a very clever idea. So let us put the n equal to 1 super Young mills in a box of size L times L times L with the periodic boundary condition in each direction. Okay. So the box, then you identify each boundary. So you can think of this as 3 torus with a periodic boundary condition. So when you read his paper, when you discover this formula as T3, you know what I mean. Yeah, it's a box with identification, basically. Okay. Now, since you have this, you introduce a further scale. You can use this scale to control the theory. So you can consider theory in 2 limits. So, given a dynamical scale, lambda, we can study the theory in the limit where L is much greater than lambda inverse, or L is much less than the lambda inverse, okay? So, in supersymmetric theory, it can be argued that the number of vacua in both limits should agree, okay? Okay. Right. So now why this is important? So look at this limit. This limit means that the box is so large, right? So you have a strong coupling as usual. But this limit the theory become weakly coupled. So one can perform an honest computation of counting vector. Observe that the argument we used earlier was a strongly coupled argument, right? We put the trace lambda lambda equal to, that you claim that there is n vector. This is a strong coupling argument. This is what we did before. Now we're going to do this in the weak coupling, in the weak coupling limit. Okay? Yes, we'll show you. Honest means that we don't have to use all these R charge or all of these anomaly. The strong coupling argument that we use. Yeah, we're gonna do the weak coupling. So to tell you before, it's like a counting holonomy. I'll show you. Okay. Yeah, we'll show you. Okay. So. Okay. Let's put it like this, okay? This I will show. Okay. This is the statement that the index doesn't depend on coupling. This is quite crucial, okay? Right. On T3, the translation P mu. So what we have to do is that we're going to quantize theory on T3, basically. This is what we're going to do. This is a primitive version of the modern version of quantizing supersymmetry on the curve space. Okay, we're going to do on the older version, which is on T3. Okay, P mu and the super translation. Well, on T3, you have to know that I impose periodic boundary condition always. Okay, and the super translation. Q alpha and Q alpha dagger are unbroken. It's enough for us to take a single linear combination of Q and Q alpha tilde and call it, I don't know how to write curly letter, Q. Okay? So we take, like you can take 1, 2, each component or whatever is your favorite, and you take whatever component, call it Q, it's fine. And we're going to use only this Q, okay? This satisfies H equal to P0 equal to Q. Forget about these Q. This, okay? Satisfying. This satisfy. Okay? the fermion number operator minus 1 to the f satisfies also this relation equal to 0. This you should have an intuition a little bit from the strong coupling side. You remember that in each vacuum you have a C2, right? Its R symmetry is spontaneously broken to Z2. What's the order parameter? Fermion number is plus, is 0 or, well, up to you, 1 or minus 1. This is the intuition you should have, at least at the strong coupling, okay? Right. Now, we consider the eigenstate E of the Hamiltonian. H. So meaning that you have H act on E equal to E. Now come to first important fact, which we'll prove later, okay? Later mean that it involves some detail to prove it, but take on trust for now. We're going to use this result, we come back to prove it later, okay? We will show that okay, and this blackboard run out, meaning I'm going to use that one. People at the back, could you see my handwriting? Yeah, okay. For E not equal to 0, a bosonic state. So you see, since fermion number is a well-defined quantity, it's anti-commute with the supercharge. So we can define what is boson and what is fermion in a well-defined way, okay? So for a bosonic state is always, remember this is E not equal to 0 only, okay? We will see that E equal to 0 is not true, this false statement. Is always paired with a fermionic state. Okay? This is first statement. We haven't shown it. It looked mysterious to you, but we'll clarify this. Pair mean that if you draw the following diagram, so let's assume that this is energy level and these are the states. Pair mean that if this is E equal to 0, okay, you can have boson. Let's dot become boson, bosonic state. And it's a fermionic state, okay? Then you can have this phenomenon where boson is alone here, but, oops, sorry. This is like this. In upper state, you can have something like that. This has to pair, this has to pair. This, you can have either boson or fermion alone, okay? If it's bosonic, you call it bosonic ground state. If it's fermionic, you call fermionic ground state, okay? So this is what I mean by this statement. Now, this we will show, of course, later. This follow directly from simply SUSY algebra, okay, on T3. It detailed, so I'll postpone it, but this is the picture you should have in mind, okay? Now, next is that a perturbation. Suppose you perturb this system in the box a little bit. Of course, if you put an excitement, boson can excite it, right? But if they move to the excited state, they have to move in pair. Otherwise, this is violated. Okay? So, a perturbation can excite certain state with E equal to 0 to become those with E non-zero, but these are necessarily composed of pairs. Okay, of bosonic and fermionic states. Is this clear? Okay. Okay. Okay, let me erase this. In other words, the perturbation, any perturbation, does not change minus 1 to the f. Well, let's write a trace minus 1 to the f. Because of this observation, Witten defined a quantity which is invariant under perturbation. This leads to the following definition. Of the Witten Index. Z of W is equal to trace. This is defined to be a trace of e to the beta h of minus 1 to the f. Okay, but observe that since there's a cancellation at the higher order between boson and fermion, it's enough to do it at the ground state. So it's a trace of E equal to 0 minus 1 to the f. This is robust quantity which is independent of the size of the box. Okay. Now there were questions why this is strong coupling and weak coupling are the same. Now you see why. Yeah, this quantity count the ground state. You see? Count the number of ground state of the theory inside the box. It doesn't matter whether you make the box large or small. These quantities are robust. It's robust. Okay, so this is the argument of the Witten Index. Okay, so now.
Just to understand what the meaning of perturbation, this quantity is equal. It's also in the strong coupling phase.
Strong or weak doesn't matter.
But in the non-perturbative effects, can you change these quantities?
No, no, it's invariant. No, this is not depend on the coupling or anything like that. This is the property of the index. Yeah. That's why people love index so much, because you can go to weak coupling and compute it, it should agree with the strong coupling. This is why people were so excited when this development came and so on. And let me state one more thing. This is the Witten original motivation, okay? Witten original motivation is that an important observation. If you understand this statement, you will extrapolate this statement to more modern index that people compute. It based on this quantity, basically, okay? If Susie is spontaneously broken, then there is no zero energy ground state. We discussed this at length, right? And so the Witten Index is 0. Okay, so this is the original motivation due to Witten. So people asked back in the time whether in any one super Young mills, whether the strongly coupled dynamics can break supersymmetry or not. So if you manage to compute this, at least in the weak coupling limit, and show that Witten index is non-zero, supersymmetry should be preserved by this statement. Okay? So next, I will compute Witten index in weak limit. We did it in strong limit already. Now we're going to do in weak limit, okay? And show that they get the same number and it's non-zero. Okay? That's right. This if-then statement, yeah? So you agree that in higher E higher than 0, they all cancel, this quantity. So it's enough to just look at this. Okay, so now let's focus on the 4D n equal to 1, pure SUNC, pure super Young mill, okay? Okay. Well, so let's look at the limit where we already, that in the limit L greater than or much larger than lambda inverse. So there exists a single vacuum for each m. This we have seen, okay? Just to review it. With m equal to 0, 1, up to n minus nc minus 1. Okay? Such that, this to remind you about this Gaugino condensation, e to the 2 pi I m over nc, okay? They are all related by Z to NC. Okay? This we have showed, you remember? And so these NC states have the same value of minus 1 to the F. Okay? Hence, we don't know it's plus or minus. This argument will not tell you whether it's bosonic or fermionic state. But we know that they have the same sign. Okay? Because of the protected Z2N symmetry, which we have shown is unbroken. Okay? Now, did you see why I'm emphasizing so much that Z2NC rotate vacua, and when you go into vacua, it's broken to Z2. This is highly important. Hence, mod CW, observe that I do only modulus, will be NC. Can be plus NC or minus NC. I don't care. Okay? Okay, this is strong coupling. Now, weak coupling gonna take the whole hour. It might look an honest computation, but it's actually subtle. It's a long statement. It's the whole 82 paper of Witten, basically, that try to explain this concept, and he shows very explicitly this thing. So I will try to review his argument back in 82 for you. Okay, right. Yes. Yeah.
But if you perform the sum in a different order, I mean, there you have a problem of conditional convergence.
Why converges? They're all number.
No, but I mean, you take a series.
Okay.
Which, I mean, each of the days will be bigger than that, right?
Why? You prefer minus? Okay, put minus. Because at the end you compute at ground state anyway. I mean, I don't know whether the original definition you want to regularize or anything like that. Yes. Did I show that gaugino condensation are low energy? It's vacuum. Hence, it's low, the lowest energy. SUSY vacuum has to have zero energy. This I show from the first lecture. Yeah, the potential has to be zero. It's annihilated by supercharge, you remember? Yeah. Yeah, it's annihilated by supercharge. You look at the note. Yeah. Right. So now we look at the limit where L is less than minus 1. Okay. The system is weakly coupled. Okay. Since non-zero electric and magnetic fields, so you have the quantity called F, right? So magnetic field contribute to the energy of the system set F mu nu equal to 0 for mu nu equal to 1, 2, and 3. Okay, because I'm on a 3 torus at the moment, okay? To have almost zero energy. So this condition make you go to pure gauge. Okay, because field strength is now 0. So now we're going to do pure gauge on the torus. This is step number 1. So because you consider at ground state anyway, any excitation you neglect, okay? You're going to focus on the lowest energy configuration as much as possible, okay? That's the motivation why we look at this configuration. Oh, we are on the torus. So you have only 3 direct. I have only 3 directions for myself, right? You mean E0? The time direction. I'm on a torus. I have only 1, 2, and 3. You can call it. I don't know. I don't know. It's different. Yeah. Okay. I understand what you mean. On the torus, how do you call which one is electric, which one is magnetic? Right? Yeah. I'm on a torus. I'm on T3. Yeah. The low energy. Oh, I can call the field strength in general. The low energy degree of freedom are therefore the commuting holonomy, right? Because you are pure gauge. You specify pure gauge by holonomy of the gauge field. Now, 3 torus have 3 directions, so there are 3 holonomy, okay? Commuting holonomy. U1, U2, U3 within SUNC, because now your gauge group is SUNC, okay? Corresponding to the X, Y, Z directions. Okay? Right. And since they are commuting with each other, you can simultaneously diagonalize them. Mm-hmm. This is too many indices. I haven't finished. 1 second. Let me erase this. Such that, of course, there are SUNC matrix, so determinant has to be 1, right? So you have to impose sum of theta mu. I put I up, right? Yes. I mu. Oh, don't confuse I in the front with index I, okay? This is complex. This is index, okay? I equal to 1 to NC equal to 0. Okay, for all mu equal to 1, 2, and 3. Okay? Right. So these holonomies are the elements of the Cartan torus of SUNC. You know the concept of the Cartan torus is the maximally commuting element in the, this is commuting element, right? In the SUNC. For those who know what Cartan subalgebra is, Okay. I think I would define it at some point. Okay. Okay. Let's see. Let me write it down first. These holonomies are elements of the Cartan torus. The subalgebra, the maximum subalgebra that commute with other elements of the, yeah. So this, okay. Please go to read it, at least Wikipedia. I mean, this you need to know, okay? Because I will have to use the condition on rank and this kind of thing, okay? But I think, okay, let's see how it goes. Okay, so there are two important points. Is that since they are maximally commuting in SU and C, so you see that there are NC minus one independent one, right? Because I impose one condition on the NC parameter. And this is the crucial point. They are all connected to the identity, which is correspond to parameter theta equal to 0, okay? This is true for SU and C. In other group, like spin 7, for example, there are another class of holonomy which is not connected to identity. And this is what Witten missed in 82. For SU and C, you are safe. There are only this class of holonomy. Okay? Okay. Now, what we can do further is that, fine. So, we look at this holonomy. So the object, so let me tell you, the main idea of this business is to count holonomy. And that's it. You manage to count holonomy, you are done with this business, okay? Now, next step is to look at Gaugino zero modes. The point is that fermion can contain can contribute to the non-zero energy configuration, okay? Non-zero Witten index, basically. So we have to look at the zero mode of these guys. So let me erase this. It's a bit long. This takes the whole hour. I can assure you, this is not an easy idea at all. I mean, but once you're familiar with it, it's a very beautiful idea. I mean, okay, the Gaugino zero mode. Take the form. So basically what you are doing is that you decompose every field into modes, okay? And you look at the lowest one in the expansion. This is called zero mode, okay? Take the form lambda alpha equal to diagonal epsilon 1 alpha. So this alpha corresponds to this alpha, okay? 2 alpha ENC alpha, where alpha run from 1 to 2 as usual. This is a fermion coordinate. And I run from 1 to NC as usual. Okay. Well, yeah, such that epsilon sum of the epsilon I alpha equal to 0 for I equal to 1 to NC. Okay, let me remark it here. I will use index I run from 1 to NC here, okay? So the same thing as before. This is the zero mode. So you might say, okay, why did I do write this? Because this is gauge field. This is Gaugino. They come hand in hand, you see? Okay. Okay. So you remember in your 101 quantum field theory, you decompose field into Fourier modes. Zero mode is the lowest one. Yeah. This is the lowest energy, basically. So in the following, okay. We treat theta AI and epsilon mu, alpha A with AB equal to 1 to n minus 1, c minus 1. Okay, let me introduce index small a, small b to be in this way. You see, if I use index I, as I used there redundancy that you have to impose the sum equal to 0. So since there are only nc minus 1 independent component, I can just write it like that, right? So you understand my notation, okay? Take your favorite component, declare it to be new variable like that. So there are only nc minus 1 independent component, okay? With AB as the R equal to nc minus 1 independent component of each quantity. Okay, here equal to nc minus 1 is the rank of SUNC, which is the maximum number of commuting generators. This is what you mean by rank, okay? And the set of this maximally commuting is called Cartan subalgebra, okay? So this is how rank appear in our context, okay? Because of the SUN condition. Okay, now, okay. So remember, we have two things. We have theta, we have epsilon. Epsilon belong to gaugino, theta belong to gauge field, okay? So let's okay, so now let's proceed as follows. We focus on the spectrum of low-lying state, meaning the state which has lowest energy, okay? These can be computing by quantizing theta and epsilon, okay? We may put the bosonic degree of freedom, theta A mu, in the ground state. And forget about them. Okay? But we must take into account of fermions. This is what Witten in his paper called Born-Oppenheimer Approximation. Okay, so he put all the boson to the ground state, and now we look at the state that can be created only the fermion. Boson now as you know, you can put always boson in the lowest energy state, but fermion there's some constraint you can do. This due to Pauli exclusion principle. And now we're gonna do Pauli exclusion principle on the fermion. Okay? The fermion can be described by the creation and annihilation operators, which I call A alpha star. This is the creation, okay? The index and A alpha A with no B, okay? Let's call B. With alpha run from 1 to 2, this fermion also, and AB run from 1 to NC minus 1, or R, okay? So now you quantize the fermion, basically, what you're doing. So you trade, now you have to define creation and annihilation operator for fermion, okay? Good. So now you have to define so-called ground state, right? So in the fermion, Hilbert space, there is a ground state, a state, which I call such that if you hit it by annihilation operator, A, alpha B to omega, you get 0, okay? So the non-trivial state, you have to hit it by creation operator. Of course, this is quantum mechanics, right? So, okay. So the purpose here is to look at quantities constructed from A alpha star A that are invariant under the Weil symmetry of SU and C. Can anyone tell me what is Weil symmetry of the group SU and C is? Yeah, it's a permutation group of the NC object. Okay? So basically, you just put the creation operator and you have to do it up to permutation. So permutation symmetry is S and C. Okay? So because you already go into the Cartan subalgebra, that's why you can look at only the subgroup that permute those generators. Okay? So this is the Weil symmetry by definition. Okay. There are only two types of invariant tensor. To contract. AB indices. Namely, delta AB, right? And the other one is epsilon. You can contract it using A1, A2, up to A and C minus 1. Okay? These are the indices that allows you to contract the indices, okay? To AB indices. Now, we're going to do that. this one I'm gonna erase. Commuting Holonomy can go. Okay. Okay, and there are turn out to be two non-vanishing combination construct from A star. One has spin 0 and one has spin 1/2 r. Let's do one spin 0 first. So this was an object we call S. Now you might wonder, what is this S? It look like the previous S? Yes. This S is constructed by alpha star AB star B epsilon alpha beta delta AB. Okay. Why spin 0? Because you construct two of them, right? You contract with epsilon alpha beta, so there's no spin indices anymore, right? And then, because of the fermion nest, you can contract with the delta. It's non-zero. Okay, it's clear? And this is clear why spin 0. The other guy is spin 1/2 r, spin r over 2. Okay, this is called the S hat. Okay. You might wonder, we didn't have S hat before. So what is this guy? Okay, I'll tell you. This one has these indices. Okay, so can you guess what I'm gonna do? I put A star and then contract with epsilon. Excellent. Yeah, that's the thing. Star A1, A star. There are many A. I know when I pick these indices, it look like a mess, but I don't have letter. So A2, alpha 2, up to A R star, no, alpha R, sorry, AR, contract with epsilon, A1 up to AR. Okay, remember our NC minus 1 is our R. Okay, so this is spin R over 2. Okay, right. Now, we're ready to finish the Witten Index. I promise to you. Come to the final point and then let you have a break after this statement, okay? If omega transform, so you know that discrete group like Sn can have dimension 1 representation. Dimension 1 representation can be trivial or non-trivial, right? If omega belong to transform in the trivial representation of the Weyl symmetry, the states are omega, you construct from the S, right? Okay. Then S omega, you can do S square omega up to S to the n minus 1, S to the R omega. Okay. Oh, wait a second. Let me make one comment. Okay, this is true. But let's make one comment here. So because of the Fermi statistic, we can contract alpha beta indices with epsilon. This I mentioned. And also this is symmetric in R indices. Do you agree? Because of the Fermi statistics with anti-symmetric epsilon. Okay? So how many components are there? Huh? How many component S hat has? S hat has You good at combinatorics? It's product of it's product of 2 times 3 times 4 up to r plus 1, right? Divided by r factorial. You agree? It's a symmetric, so how do you count symmetric? This is how you do it, right? 2, 3, okay, up to over r factorial. This is r plus 1 component. We'll use this later, but okay. Let's come back to our point. This is the main point. If omega transform in the trivial representation, okay, the of the Weyl symmetry, the states that we construct are these guys. This is invariant under Weyl symmetry. Okay, you agree? There's no indices left and so on. And these are in the trivial representation. Okay? So now, how many of these states are? R plus 1, which is, what is R? NC minus 1, so R plus 1 is NC. Now you see, in this case, Witten Index is NC. So, okay. So let me write here. We're almost done. So we already obtained the set of the states, which are Y invariant, non-zero. You might wonder, what about the S hat, right? It will come later. So let's count these guys first. They are all bosonic. You agree? So ZW is equal to trace of 1 minus F, right? We already at the ground low-lying state, so no need for E equal to 0. We know what we are doing. And this is NR plus 1, which is NC. Miraculously matched with the Song coupling. However, this is only one set of states. There are another possibility. As I said, group Weyl symmetry, Weyl symmetry can have also non-trivial representation of dimension 1. So we have to analyze that also, this next step, okay? Yeah, we forget them because we already put them in a ground state.
But we are counting ground states.
They're already in ground state. They could not contribute anymore. I mean, we only count the fermion is the non-trivial one here. So we have theta and epsilon. You remember I said that since we can put all of them to the ground state and forget about them. This is Born-Oppenheimer approximation.
You can put them all in the ground state, but I don't understand why you can forget them if you are counting ground states.
Yeah, they
So if they are ground states,
they have they could.
Why are you sure that the bosons have a unique ground state? That the thetas, why are you sure that the thetas have a unique ground state?
Omega or theta?
Theta.
Ah, you mean why theta has the ground state?
Why is unique?
Why is unique? Okay, so basically, what I'm saying is that, let me see. So basically, well, in the condensation, okay, you agree with me that you can always put the boson in there.
I can put them either here or here.
You're at weak coupling at the moment. So you're on T3 at the moment, right? I don't see any non-trivial potential that you can do for this guy, right? These are first of all, these are zero mode. So you can take the zero mode of the boson component and you can declare it to be the starting value of your ground state, whatever value you have, which in general you can set to 0. It's boson, it's no harm. Fermion, you cannot do that in general. Okay? It give the 0 point where you want to set it to 0. And you can do it at any number of boson actually. And this is what we do. Okay? Now, let me finish the argument of the omega. Indeed, as you point out, we only deal with the fermion. Observe that there is no boson involving in this game at all. We already construct that everything construct by A star. Okay, A star can have spin 0. Okay, these are our bosonic state these are bosonic, non-trivial bosonic that contribute to the zero energy. Okay, the theta don't. These do. The S do. These are crucial point. Okay, and S corresponds to the gaugino, and this is why we look at gaugino, zero mode. Okay, the gauge field zero mode, you forget about them. Okay, if omega is transformed in a non-trivial one-dimensional representation. Can anyone tell me why it has to be either trivial representation or non-trivial dimensional representation? Has to be one-dimensional. Why? Because it doesn't carry index. It cannot be in more than one-dimensional representation, right? So one-dimensional representation can either be trivial or non-trivial. Okay, so if this is non-trivial, this state itself cannot be physical. Can anyone tell me why? Yeah, it's not pi-invariant. Ground state cannot be invariant. It carries charge, discrete charge, basically. And this violates so-called the Gauss's law, right? Okay, but we can make true invariant with S hat. Basically, S hat contains the epsilon tensor of the A indices, you see? So any one-dimensional representation non-trivial, like for example, it can flip like a reflection. It can compensate by the epsilon. This is why. So if you construct this state, you will have S hat of alpha up to alpha r act on omega. Okay? How many states are there? R plus 1. These states, these are plus 1 states, have spin R over 2. So the Witten index is ZW equal to trace minus 1 to the F equal to, so they can be either fermionic or bosonic, right? Depend on R. If R is odd, it is fermionic, right? Times R plus 1. You agree with this formula? So this is minus n minus 1 nc. So up to a sign, this is nc. Again, if you take a modulus, which we take, in any case, it is nc. Okay? Oh, okay. So we can have a break here if you want. And I will make a comment on these results later. And in the meantime, if you have questions on any technicality, I'm happy to explain in the break, okay? Okay, so what we have seen so far is that we show that Z of W is equal to rank plus 1 equal to NC, okay? So is rank plus 1 is true in general? It's turned out not. This is turned out to be very special for SU and C. I emphasize that if you do, for example, spin 7, this is violate this thing. So rank plus 1 is going to be only 7. Rank of it is, so basically spin 7 is SO7. It has rank 3. So rank 3 plus 1, you get 4. But this is not the right number. In general group, it's a dual Coxeter number, as I stated earlier. This is because the holonomy, which we count, connected to identity. And there is another set of holonomy which is not connected to identity. So I leave you as an exercise. This is in section 7.3.2 in my note. Please read it, and you will understand why for general group there are more subtleties than SUN. Okay, but I would like to do only SUN, and since this is non-zero, it's not spontaneously breaking supersymmetry. Okay, so this is another point. Now, come to the point that I promised to you. I don't know you forgot or not to remind me to do it. Is the pairing of the bosonic and fermionic state. Okay? So now, let's do this. So the whole thing that we did hinge on this point. Okay? Pairing of the bosonic and fermionic states for E not equal to 0. This is a bit off topic, that's why I do it later. So you can draw the following diagram. So you start from E. You can choose to hit it by Q or Q dagger. Okay? So this is, how do you call it, descendant? Okay, of this thing. And then you can also do another one. Minus Q dagger times E. Okay? So you only have these states. Okay? So this is the multiplet structure which you can construct from QQ tilde. The other one is just a follow from the commutation relation. Okay, they are equivalent to these four guys. Okay, right. So the argument goes as follows. If QE or Q dagger E is 0, the multiplet has two states. Okay? If both of these guys are 0, the multiplet has one state. And in addition, for this case, you can also show that E is 0. Why? Because if you do look at this equality, this is a trick that we used earlier. Square plus QE square, right? If both of these guys are 0, then E has to be 0. This you agree? So, the only case, this case, is a E equal to 0 case, okay? But we want to prove it for non-E0, so this either 4 state or 2 state, so they're paired, okay? This is clear? Okay, so this finished the proof. This case is E equal to 0 case. We don't consider. This is 4 state or 2 state. Doesn't matter. They pair. Okay. Okay. So next, we're gonna add matter into our gauge theory. This is what many people were asking me about earlier. Oh, what happened if you add matter? What about anomalies? What about running and so on? Okay. So now, yes?
So the argument really relies on the fact that it's on a torus, right?
Yeah, definitely.
Could it be that we lose something? I mean, what do we learn about Minkowski? Is it really...
Minkowski is hard because you don't have the L. Well, you see, the counting that we did is a weak coupling counting. Yeah? So you have to have a scale to suppress the lambda inverse in that sense. Yeah, with a periodic boundary condition to preserve supersymmetry. You see, we need to preserve supersymmetry because we use one supercharge, right? The curly Q to do everything on this blackboard, basically. So at least you have to have that supercharge left for me. Otherwise, I cannot do anything.
But because yesterday's argument was in Minkowski's space, right?
Yesterday, yes. Yesterday, the strongly coupled is in Minkowski space, yes. But the point is that even when you put it in a torus as strong coupling, nothing changed. Yep. Okay. You can ask me, can you do it on any other manifold? Yes. Later we will do on, well, usually this can be done also on S2 times S1, for example. Yeah, not necessarily conformal. We will demonstrate this to you. That you can even do it with a not a non-conformal theory. But the point is that whether you can have the same interpretation as Witten Index or not, this is not the same, not always the same. Okay. But to choose manifold that preserve supersymmetry, this is highly non-trivial subject. Okay. Well, this is the whole research basically that was. A few years ago was people, there was also a nice set of review by now, like you heard of Festuccia Seiberg and his literature. So which manifold that you can put rigid supersymmetry on and what's the condition, what's the supercharges you can have in those manifold and what's the supersymmetry algebra. That's a very non-trivial subject, okay? Okay, so I think Witten Index really teach us a lot. I mean, about doing things at weak coupling and strong coupling and match them. And this is a very instructive example. Yeah, indeed. I mean, the point of this school is to bring you to the frontier of the research, right? I mean, and this is a really important topic in my opinion. Oh, there were a question. That what about boson that I put in the ground state? Which ground state do I put in? You can put it in omega, for example. This is fine. Okay. This is you always have this thing. You can put them to this one. Okay. It's a what? Sorry. For non-zero energy, okay, so
this argument is specific to torus or is hold for every manifold?
Sorry, I don't understand.
So this pairing of bosonic and Baryonic state
Yeah.
for non-zero energy.
Oh, non-zero energy, right? Okay.
Yeah. So this is specific to torus or it holds for any manifold?
Ah, good, excellent. So it's true if provided you have commutation relation that I wrote down. So first of all, I define one combination of supercharge. If you choose a manifold with one supercharge, such that the P, you remember the Hamiltonian is QQ dagger, with commutator such that -1 to the F anti-commute with Q. If those relations are true, these are true. Okay? I use only that. Specific to torus or not, this I don't know. Yeah, but maybe if you can define a manifold which has similar algebra, you have to do this multiplet analysis again. Okay? Okay, so let's move on to supersymmetry Qcd. So I have time to 11, okay. So you have SUNC gauge group, NF matter, NF chiral multiplet in fundamental of SUNC, NF chiral multiplets in the anti-fundamental of SUNC, and you set superpotential to 0. This is define what my theory is. Okay? From now on, I will keep drawing this picture. NC, NF, and NF. Okay? I'll explain to you what this means. So, this diagram, circular node, means that I have SUNC gauge symmetry. This means that you have NF arrows going out mean that it's fundamental. NF means you have NF copies of them. Going in means anti-fundamental. You have NF of them. Okay? Is this picture clear for you? So if I draw this picture, it means this. And of course, I have to supplement with this. This picture doesn't tell you what the superpotential is. I have to supplement of this. This has a name. It's called quiver theory. You don't need to know it. It's just convenient. But it's so convenient that when you compute anomalies, this can help you. Okay? Right. So the action of this theory, of course, we are learning, so we have to talk about action and everything of this theory is SQCD, action of SQCD is equal to S gauge plus S kinetic. Okay? S gauge is as before. Oh, I should lift it. Okay, so S gauge is as usual. Okay, so now S kinetic. First, I will write in superfield, and I will write in components. Okay, so superfield is this one. Okay, so now it's time to explain to you this notation. So when you have SUNC gauge group, they are in the fundamental. So let me call this guy Q. Let me call this guy Q tilde. Okay? So how many indices Q and Q tilde have? It will carry the gauge index, okay, in the fundamental representation. So in my convention, oh dear, I put it up. I never keep this consistent, so remind me if I'm not consistent with myself, okay? A run from 1 to NC. I'm sorry, this is my color index. Okay? And since I have many NF copies of them, I have to deal with each of them one by one, right? So I have also index I. I will use AB in general for A. and ij run from 1 to nf. Okay? These are going to be my notation. Okay? So when you dagger, you have to swap them because they are in conjugate representation to they are complex representations. You have to conjugate. When you conjugate, index go up or down. Okay? So this, and then you have e to the v. E to the v is a vector multiplet. The vector superfield, if you remember, they contract with AB and Q with AI, okay? Plus Q tilde dagger. Now you see Q tilde dagger, you have to swap up and down. E to the V, BA, and Q tilde IB. This is how you write superfield coupled to the gauge field, okay? So this is why we introduced V in a previous lecture. Now, if you hate this, I can write down it for you in components. Okay? So S kinetic is sum of I to 1 to NF d4x. Then you do d mu q tilde. Okay, now it's getting too much for me. I'm going to drop some indices, okay? The color one I will drop. I d mu qi, okay? Plus the fermion term, writing in two components is look like this. The F auxiliary term look like this. Then you have the Q coupled to the fermion and lambda. With the lambda, oh, I'm bored. Plus Q tilde I dq. D is a d auxiliary field. And plus, I'm run out of space, so I'll continue here. Q goes to Q tilde, psi goes to psi tilde, F go to F tilde. Look at the note, please. I mean, this is the price you pay writing things in component, but okay. It's explicit, but it's long. So this part is the kinetic term for the bosonic component of the Q. Okay, they're complex. So you have to write it like that. This is a fermionic partner of the Q. Okay? This is the auxiliary field, the highest component in the multiplet of the Q. Okay? This is Q coupled to Gaugino. This is again the same. This is Q coupled to the D. D is the auxiliary field in the vector multiplet. And then you do the tilde part. You do the tilde part. Okay? Exercise, balance the indices. It's not hard, it's just up or down, right? I mean, when I fix the flavor for you, just put the flavor color in opposite way. And everything was balanced, okay? So I think that is the part. But okay, let me not mess around with these components or this kind of thing. My life is not about doing algebra, okay? So I'm going to do dynamics. This is the focusing point of our lecture. So before we doing quantum theory, we have to understand the classical theory. This is always have to do this in order, okay? If you don't understand classical physics, don't even attempt to do quantum physics, okay? This is a philosophy. So we're gonna have to do first, what's the global symmetry we have? Okay, so you can assign global symmetry in a naive way as follows. The way I will assign global symmetry will be the same way as I did in the earlier lecture. So let's do this table. Let's UNC, right? So look at this diagram. You can almost read everything off from that already. So as UNC, you see that Q is NC. Okay, I have some problem. This is a problem of convention. I never get this thing right. I'm sorry. It's up to you, okay? Whether you want to call this Q or Q tilde. my note, I call this Q with the index. Now I don't remember AI with the IA. Okay. So in this notation has a price. So Q going in, so it's in the bar. If it's going out, it's in NC. Okay. Some of you already hate me. If you call this quark, how come it's in the anti-fundamental representation? But it doesn't matter. It's a conjugate representation. You take whatever you want. Okay. Now look at NF. There are two NF that rotate these guys, right? You see these two NF? You put NF of them. Since these are complex fields, they have to rotate in SU and C. Okay, depending on what you want to call. This is NF number 1. This is 2. Okay? So NF1 is going out. So it is NF. This is singlet. This is singlet. This is in NF bar. Do you agree? I will use this convention. No, this is fine. So if it's going in, it's bar. If going out, is non-bar. Okay? Again, each chiral field, you can assign U1 to them. Okay? So you have two chiral fields, right? U1 associate with Q and U1 associate with Q tilde. And you remember how we do this? We assign charge 1 to this, 0 to this, 0 to this, and 1. Right? So these are the classical global symmetry. This is gauge symmetry. This is chiral field. Okay? There is another one.
I just want to just make the comment that in fact the symmetry is UNF and you just put the U1.
Yes. I decided to separate it. Yes. Thank you. Yeah, you can call it UNF if you want. Yes. Because this is NF charge 1. Okay? Okay. Now the point is that it's more convenient to do this. You see why. There is another one, in fact. Could you remind me what is the other symmetry? R symmetry. Okay. The R symmetry, as I told you, in classical physics, nothing fixed R symmetry for you. You remember this? You can take it to be any values, in fact, such that only actually there are two. The superpotential has charge 2, but this is 0, so you cannot do much. The other constraint is what? Gaugino has to have charge 1. Okay? Symmetry, which I will call it U1X for now. You might wonder why I come up with this weird name. Yeah, I will tell you. It rotates fermion as like this. So, okay, such that the X charge of Q is 0, X charge of 0 of Q and Q tilde. Let me, and X charge of the thing is this. Okay. Can you tell me what is X charge of psi and psi tilde? The partner of the Q. -1. Okay. Excellent. So this is our classical symmetry. I emphasized 3 times already classical. In quantum, everything can happen with them. They can be anomalous, can be broken, or this kind of thing. Okay, so we will study that soon. Right. Now, it's not conventional to use these charges. This we should conform to the QCD literature, of course. I mean, so you define the following. You define 2 symmetry as baryonic symmetry, and you define another one called axial symmetry to conform the convention of the literature, basically. How do you define baryonic symmetry? It's a U1. We call it U1b, okay? U1b I define to be a linear combination of Q and Q tilde. Now you understand why I have to separate Q, U1Q out of the UNF. And U1A is conventionally to define it as U1Q minus U1Q tilde. This is convention, okay? Oh, I'm wrong. Sorry, I mean this one. Okay, so let's correct our table. I don't want to use this combination anymore. I prefer the new combination for some reason, okay? So this is B and A. So what's the B? You take combination of minus, right? So this is 1, this become minus 1, and A is 1 and 1, okay? Okay, now I think I should mention about this. Since we are doing classical physics, we have to understand this. So the classical, so you can ask me, how about the vacuum of this theory? The vacuum of this theory, it's almost 11, right? I should finish at 11, am I right? Okay, let's see. Okay, so let's define the classical moduli space. And we continue next time. I don't think I will finish it. So the classical moduli space, you have to minimize the potential as usual. And the potential coming from two parts, the D part and the F part. Okay? So the D part, you remember how you write down the scalar potential? You take the F part is derivative of superpotential mod square. The D part is this guy. You have seen this. You just take this part from the action. You remember this part, right? And the F part was this guy. Okay, and then you write down equation of motion of this guy so that you find that the D is this guy. This is the group generator writing in the fundamental representation, okay, of Q dagger IA Q BI minus Q tilde BI Q tilde IB, IA, okay? And F is set to 0. So this is equation of motion, okay? This has a name. This is called the D-term equation, or simply D-terms, okay? So for those of you who told me from the first lecture that in supersymmetric theory you have to solve the vacuum, not just F term, the D term. Here's the D term. Okay. Right, and then you solve equation where V supersymmetric vacuum just tells you that this has to have solution where V equal to VD equal to 0, right? So this means that you have to have Q tilde A Q BI minus Q tilde IA Q tilde BI equal to R delta AB. for some are real. Okay. So this is the condition for our supersymmetric vacuum. So I think I don't have time to solve it in front of you now. So I think next lecture we're going to do this classical vacuum of this theory. It will divide into two cases when number of flavor is less than color and greater than or equal to. Okay? And then we see that the two physics of these two are highly different. And then we move on to quantum mechanics when we understand classical physics of this theory. Okay? That's the plan. Thank you very much.